Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, to let the day begin releasing its hold on you. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cosy corner where darkness has settled in and you're finally ready to rest? Tonight we're going to explore one of the most beautiful and bewildering questions in all of cosmology. The universe is expanding, but what is it expanding into? It's a question that seems simple on the surface, but opens into something wonderfully strange when we look closer. We'll discover what expansion actually means in the context of space itself, understand why the question might be based on a misunderstanding of reality, and contemplate what it means for space to grow without needing anything to grow into. It's a journey that spans the entire history of the cosmos and challenges our most basic assumptions about existence. But don't worry, this isn't going to be an anxiety-inducing exploration of cosmic horror or existential dread. Instead, we'll move slowly and carefully through the mathematics, the observations, the philosophical implications, taking our time with each discovery. By the end, I think you'll find a strange kind of peace in realizing that the universe doesn't need our permission to be stranger than we imagined. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with your quiet hours. So settle in, let your shoulders drop away from your ears, take a slow breath, and then another. And let's begin our slow drift through this beautiful puzzle. There's nowhere you need to be right now, nothing you need to solve. Just listen and let the story unfold and know that it's perfectly fine if your eyes close before we reach the end. Let's start with the question itself, because it's more slippery than it first appears. When someone asks what is the universe expanding into, they're doing something perfectly reasonable with language. They're taking their everyday experience of expansion and trying to apply it to the cosmos. A balloon expands into the air around it. A city expands into the countryside. Water expands into ice, taking up more space in your freezer. In every case we encounter in daily life, expansion means something is growing into a pre-existing space that was already there, waiting. So when astronomers tell us the universe is expanding, our minds immediately reach for that same framework. If the universe is getting bigger, there must be something it's getting bigger into, right? Some vast emptiness that was there before, some container that holds everything. It's such an intuitive leap that questioning it feels almost silly. Of course, there has to be something beyond the edge, something that the universe is expanding into. The alternative seems to make no sense at all. But here's where language starts to fail us, where our everyday experience becomes a misleading guide. The universe isn't expanding into anything, because there is no anything for it to expand into. There's no pre-existing space, no container, no void waiting beyond the edge. And this isn't because we haven't discovered what's out there yet, or because our telescopes aren't powerful enough to see it. It's because the concept itself is based on a category error, a misunderstanding of what expansion means in this context. When cosmologists say the universe is expanding, they mean something more subtle and strange than objects moving apart through space. They mean that space itself is growing, that the fabric of reality is stretching, that the distances between galaxies are increasing not because the galaxies are travelling through space, but because new space is being created between them. It's not expansion into something, it's the expansion of something, of the only something there is. To understand why this matters, we need to think about what space actually is. In our everyday experience, space seems like an empty stage where things happen, a neutral background that was there before objects arrived and will remain after they leave. We move through space, we measure distances across space, but space itself seems unchanging and absolute. This intuition is so deep that even thinking about space as something that can change, that can have properties and behaviours of its own, feels deeply weird. But general relativity, Einstein's theory of gravity, revealed something remarkable. Space isn't a passive stage. It's a dynamic participant in physical reality, something that can bend and curve and stretch and compress. Mass and energy tells space how to curve, and curved space tells mass and energy how to move. Space has geometry, and that geometry can change over time. When we say the universe is expanding, we mean that the geometry of space itself is evolving, that the metric that defines distances is growing. And here's the crucial point, the one that dissolves the original question. If space is all there is, if there's nothing outside of space because quote-to-quote is itself a spatial concept, then expansion doesn't require anything to expand into. The universe doesn't need a container because the universe is the container, and the container is getting bigger, and there's no contradiction in that because there's no external reference frame from which to judge the growth. This brings us gently to our first real insight. The question quote 3 assumes that expansion requires an external space, a beyond. But if space itself is what's expanding, if there is no beyond because beyond is a direction in space and space is all there is, then the question dissolves. It's not that we don't know the answer, it's that the question was asked in a framework that doesn't apply to reality. Before we go deeper into the theory, let's ground ourselves in what astronomers actually observe, because the evidence for expansion is overwhelming and beautiful in its simplicity. In the 1920s, Edwin Hubble made measurements that changed our understanding of the cosmos forever. He looked at distant galaxies and measured two things: how far away they were and how fast they were moving relative to us. What he found was a clear, undeniable pattern. The farther away a galaxy was, the faster it was moving away from us. This wasn't a small effect or a subtle correlation, it was a dramatic linear relationship. Galaxies twice as far away were moving away twice as fast. Galaxies 10 times as far away were receding 10 times as fast. It was as if something was pushing everything apart, as if the entire cosmos was involved in a vast coordinated retreat. But here's what's crucial to understand. The galaxies weren't moving through space at these enormous speeds. If they were, we'd see different patterns, different behaviours. Galaxies that were moving through space would show signs of that motion in other ways. They'd have particular velocities that didn't necessarily correlate with distance. They'd disturb the space around them. What Hubble saw was different. It was a pattern that made perfect sense if space itself was expanding, carrying galaxies along with it like raisins in a rising bread. Let's pause with that analogy for a moment, because it's useful even though it has limitations. Imagine baking bread with raisins distributed throughout the dough. As the bread rises, the raisins move apart from each other, but the raisins aren't moving through the dough, they're being carried by the expansion of the dough itself. A raisin near the edge of the loaf moves farther from the centre than a raisin near the middle. Not because it's moving faster through the dough, but because there's more dough between it and the centre. And all of that dough is expanding. From any raisin's perspective, all the other raisins are moving away, and the farther away a raisin is, the faster it appears to recede. There's no centre to the expansion from within the dough, no special raisin that everything is moving away from. Every raisin sees the same pattern, the same relationship between distance and recession speed. This is exactly what we observe in the universe. Every galaxy sees every other galaxy receding, with speed proportional to distance, and there's no centre to this expansion in the three-dimensional space we can observe. The measurement that reveals this expansion is redshift, one of the most important tools in astronomy. Light from distant galaxies is stretched as it travels through expanding space, shifted toward longer, redder wavelengths. The amount of redshift tells us how much the universe has expanded during the light's journey. A galaxy with a redshift of 1 has light that's been stretched to twice its original wavelength, meaning the universe has doubled in size since that light was emitted. It's a direct measurement of cosmic growth. When astronomers plot galaxy redshifts against distances, they find that beautiful linear relationship Hubble discovered. The slope of that line, known as the Hubble constant, tells us the current rate of expansion. Today we measure it to be about 70 kilometers per second per megaparsec, which means that for every million parsecs of distance, roughly 3.26 million light years, galaxies are receding from each other at an additional 70 kilometers per second. It's not a huge speed when you first hear it, but over cosmic distances, it adds up to something magnificent. And the pattern holds across the entire observable universe, across billions of light years, encompassing hundreds of billions of galaxies. Everywhere we look, we see expansion. The universe isn't static and eternal. It's dynamic and evolving, growing larger with every passing moment. Space itself is stretching, distances are increasing, and what we're witnessing is the aftermath of the universe's beginning, an expansion that started nearly 14 billion years ago and continues today. Which leads us naturally to consider what this expansion implies about the past, about where it all came from, about the moment when expansion began. If the universe is expanding now, growing larger with each passing moment, then logic suggests it was smaller in the past. Run the film backward, reverse the expansion, and galaxies that are currently billions of light years apart come closer together. Go back far enough, and they overlap. Go back farther still, and everything in the observable universe occupies a smaller and smaller region of space. This is the unavoidable implication of cosmic expansion, and it leads to the most profound conclusion in all of science. The universe had a beginning. There was a moment, finite time in the past, when everything we can see today was compressed into an unimaginably small, hot, dense state. This is what we call the Big Bang, though that name is somewhat misleading. It wasn't an explosion in space, it was the beginning of space itself, the moment when expansion started, when time began, when the universe came into existence. Every atom in your body, every photon of starlight, every galaxy in the cosmos traces its origin back to that initial state. The evidence for this is written across the sky in a phenomenon called the cosmic microwave background. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that moment, space was filled with a hot plasma, opaque to light, photons constantly scattering off free electrons. But when atoms formed, when electrons settled into orbits around nuclei, photons were suddenly free to travel without scattering. The universe became transparent. Those photons have been travelling ever since for nearly 14 billion years, stretched by the expansion of space from visible light to microwaves. Today, we can detect them coming from every direction in the sky. A faint glow at a temperature of about 2.7 degrees above absolute zero. This is the oldest light in the universe, the afterglow of the Big Bang, and its properties tell us an enormous amount about cosmic history. The cosmic microwave background is remarkably uniform, the same temperature in every direction to within 1 part in 100,000. This tells us that the early universe was extraordinarily smooth, with only tiny variations in density from place to place. But those tiny variations mattered, because gravity amplified them over billions of years, turning slight overdensities into galaxies and clusters and the vast cosmic web we see today. The pattern of those primordial fluctuations is imprinted in the microwave background, a snapshot of the universe as a baby. When we run the expansion backward beyond the formation of atoms, we enter an era where the universe was so hot that even nuclei couldn't exist. Protons and neutrons floated free in a soup of particles and radiation. Go back farther, before the first second, and the temperature was so extreme that even protons and neutrons broke apart into their constituent quarks. The universe was a plasma of fundamental particles, governed by physics we're still trying to fully understand. This is where things get truly strange, where our understanding becomes more speculative and provisional. What happened in the first tiny fraction of a second? What was the state of the universe when it was smaller than an atom? when all the energy we see distributed across billions of light years was concentrated in a space smaller than the period at the end of this sentence. General relativity suggests there was a singularity, a point of infinite density and infinite curvature, but physicists suspect this is where the theory breaks down, where we need a quantum theory of gravity to really understand what happened. And this brings us back, in a way, to our original question about expansion. If we can trace cosmic history back to an initial state of extreme density, what was there before? What did the Big Bang expand into? Was there a pre-existing void, a space that the universe appeared within? The answer, strange as it may seem, is that these questions may not make sense. If time itself began with the Big Bang, then there was no quote _4 _. If space itself emerged from that initial state, then there was no quote 5 for the universe to appear in. Let that thought settle as we continue. The universe might not have expanded into anything because there was nothing, in the most literal sense possible, for it to expand into. The expansion created space rather than filling space, and this distinction is what we'll explore more deeply in the chapters ahead. Let's try another analogy, one that might help us think about expansion without an outside. Imagine the surface of a balloon, not the three-dimensional rubber, but just the two-dimensional surface. Draw dots on that surface to represent galaxies. Now inflate the balloon. As it expands, the dots move apart from each other. The distance between any two dots increases as the surface stretches. Now here's the key question. What is the surface of the balloon expanding into? From the perspective of a two-dimensional being living on that surface, a creature that can only move and perceive in 2 dimensions, the answer is nothing. The surface isn't expanding into any space that the being can access or conceive of. It's simply getting larger, distances are increasing, but there's no third dimension for the surface to expand into as far as the 2-dimensional being is concerned. Of course, we can see from our 3-dimensional perspective that the balloon is expanding into the room, that there's a third dimension that the surface is stretching through. But that third dimension is completely inaccessible to the 2-dimensional being. It's not part of their reality. From their perspective, living entirely within the 2-dimensional surface, expansion happens without requiring any external space. The surface is all there is, and it's getting bigger, and that's the complete description. This is the analogy cosmologists use to help us understand cosmic expansion. Our universe might be like that 2-dimensional surface, except we're dealing with 3 spatial dimensions instead of 2. Space itself is expanding, getting larger, but it's not expanding into anything that we can access or detect because there's no 4th spatial dimension for it to expand into. Or if there is such a dimension, it's as foreign to us as the 3rd dimension is to the 2-dimensional being on the balloon surface. The balloon analogy has another nice feature. Notice that the surface of the balloon has no edge, no boundary. A 2-dimensional being could travel in any direction forever and never reach an end, never fall off the edge of their universe. They'd simply loop back around to where they started because the surface is finite but unbounded. This might be true of our universe as well. Space might be finite in total volume but have no edge, no boundary, no place where you could say, quote 6, quote, but we have to be careful not to push the analogy too far because it has limitations. The balloon surface is curved. You can measure that curvature by drawing triangles and finding that their angles don't add up to exactly 180 degrees. Our universe, as far as we can measure, appears to be flat or very nearly so. Triangles drawn across cosmic distances have angles that add up to 180 degrees within our measurement precision. This suggests that if the universe is finite like the balloon surface, it must be so enormously large that the curvature is too subtle to detect. There's another possibility, though, one that's perhaps even stranger. The universe might be infinite, not just really big, not just larger than we can observe, but actually infinite, extending forever in all directions with no edge or boundary. If this is true, then the universe was infinite even at the Big Bang, and it's been infinite throughout its entire history. Expansion doesn't mean going from finite to infinite. It means that distances between objects in an already infinite space are growing over time. This is hard to wrap your mind around. The idea of an infinite universe that's expanding. If it's already infinite, how can it get bigger? The answer is that even in an infinite universe, the density can change. Imagine an infinite grid with galaxies at regular intervals. Now increase the spacing between grid points. The grid is still infinite, it still extends forever, but the density has decreased. The average distance between galaxies has grown. This is what expansion means in an infinite universe. Whether the universe is finite but unbounded like the balloon surface, or infinite and extending forever, the key insight remains the same. Expansion doesn't require an external space to expand into. It's the stretching of space itself, an internal property of the geometry, something that happens within the universe rather than requiring anything beyond it. The question, what is it expanding into, assumes an external reference frame that doesn't exist, a perspective from outside space itself, and this connects to something equally important about the nature of the Big Bang, which we'll explore as we move forward into our next discovery. One of the most persistent misconceptions about the Big Bang is that it was an explosion that happened at a point in space, a specific location where everything began and from which everything is now moving away. People imagine a vast cosmic blast radiating outward from some centre, and that all the galaxies we see are fragments flying away from ground zero. This picture feels intuitive. It matches our experience with explosions, but it's completely wrong in almost every important way. The Big Bang wasn't an explosion in space, it was an explosion of space. Expansion began everywhere at the Big Bang, compressed to extreme density. When expansion began, it began everywhere at once, and every point in space has an equally valid claim to being the centre of the expansion, which is the same as saying there is no centre at all. Think about the raisin bread analogy again. When the bread rises, there's no special raisin at the centre of the expansion. From every raisin's perspective, all the other raisins are moving away, and the raisin itself appears to be at the centre of that motion. The same is true in the universe. From our galaxy, we see all other galaxies receding from us with speeds proportional to distance. But an observer in any other galaxy would see exactly the same pattern, with all galaxies receding from them. There's no privileged location, no cosmic centre. This is one of the profound implications of general relativity and the cosmological principle, the idea that the universe looks roughly the same from every location on large scales. If the universe is homogeneous and isotropic, meaning it has the same properties everywhere and looks the same in all directions, then every observer sees the same expansion pattern. Everyone can consider themselves at the centre, which means the concept of a centre becomes meaningless. The universe has no edge and no centre in the spatial sense we normally use those terms. So where did the Big Bang happen? It happened here, where you're sitting right now reading these words. It happened at the location of the Andromeda Galaxy, 2.5 million light years away. It happened at the position of the most distant galaxies we can see, more than 13 billion light years away. Every point in space can trace its history back to the initial hot, dense state. The Big Bang wasn't somewhere else. It was the beginning of everywhere, and everywhere includes here. This helps explain why we see the cosmic microwave background coming from all directions. Those photons didn't originate from a distant explosion we're looking back at. They originated from the hot plasma that filled all of space 380,000 years after the Big Bang. As space expanded, the region that emitted the photons we detect today was stretched away from us in all directions. We're inside the emission region, not outside looking in. The microwave background forms a sphere around us not because it came from a spherical shell, but because we're seeing light from the moment of last scattering in every direction we look. The geometry of this is subtle and takes some thinking to fully appreciate. When we look at the cosmic microwave background, we're looking back in time to when the universe was much smaller and denser. The photons we detect today have travelled for nearly 14 billion years through expanding space. The regions that emitted those photons were much closer to us back then, but they've been carried away by expansion to enormous distances now. If we could instantly see where those regions are today, they'd be vastly farther away than the light travel time suggests, pushed to distances greater than the observable universe's radius by the expansion that occurred while the light was travelling. This brings us to something important about horizons and observability. We can't see the entire universe, only the portion of it from which light has had time to reach us since the Big Bang. This is called the observable universe, and it's a sphere around us with a radius of about 46 billion light-years. That's larger than you might expect for a universe that's only 14 billion years old, and the reason is expansion. Space has been stretching while light was travelling, so the regions we see today have been carried to greater distances than light could have travelled in 14 billion years through static space. But beyond our observable horizon, the universe continues. There are galaxies out there, presumably, that we will never see because the light from them hasn't had time to reach us yet. There might be infinitely many such galaxies if the universe is infinite. And all of those distant regions experienced the same Big Bang we did, the same beginning, the same initial conditions. The Big Bang wasn't localized, it was universal in the most literal sense. And this brings us gently to a realization about perspective and observation. We're not looking at the universe from outside, we're part of it, embedded within it, observing it from within the very fabric that's expanding. Our understanding of cosmic expansion comes from measurements made within the universe, from watching how space behaves from the inside, and this is the only perspective we have, the only perspective that exists. To understand why the universe doesn't need anything to expand into, we need to look at the equations that describe how space itself behaves. General relativity, published by Einstein in 1915, revolutionized our understanding of gravity by revealing it not as a force, but as a manifestation of curved space-time. Matter and energy tell space-time how to curve, and curved space-time tells matter and energy how to move. This elegant reciprocal relationship is encoded in Einstein's field equations, 10 coupled nonlinear partial differential equations that are beautiful, profound, and notoriously difficult to solve. When Einstein first wrote down these equations, he was thinking about gravity in the context of stars and planets, local phenomena where space-time curves around massive objects. He wasn't initially considering what the equations might say about the entire universe. But soon after publication, other physicists began exploring cosmological solutions, asking what happens when you apply general relativity not to individual objects, but to the universe as a whole. The first cosmological solution was found by Willem de Sitter in 1917. He discovered a solution describing an empty universe, devoid of matter, that nonetheless expanded exponentially. This was a surprise, a hint that space-time itself could be dynamic, even without matter to curve it. But it was Alexander Friedmann, a Russian physicist and mathematician, who made the breakthrough that truly matters for our story. In 1922 and 1924, Friedmann found solutions to Einstein's equations describing universes filled with matter and energy that could expand or contract over time. Friedmann made some simplifying assumptions that the universe is homogeneous, meaning it has the same density everywhere, anisotropic, meaning it looks the same in all directions. These assumptions, which seem reasonable on large scales and are supported by observations, lead to a specific form of the space-time metric, a mathematical description of distances in an expanding universe. The Friedmann equations describe how the scale factor of the universe, essentially a measure of how stretched space is compared to some reference time, changes over time based on the density and energy content of the universe. These equations revealed something remarkable, a static universe, one that neither expands nor contracts, is unstable in general relativity unless you add an extra term, a cosmological constant that acts as a kind of repulsive gravity. Einstein himself had added such a term to his equations specifically to allow for a static universe, because in 1915 nobody imagined the cosmos might be changing. When Hubble discovered cosmic expansion in the late 1920s, Einstein reportedly called the cosmological constant his biggest blunder. Though interestingly, it's made a comeback in modern cosmology for entirely different reasons we'll explore later. What the Friedman equations show is that space itself is dynamic. The scale factor evolves over time, growing or shrinking depending on the universe's contents. Expansion isn't something that happens to objects in space, it's something that happens to space itself. The metric that defines distances is time-dependent, and this time dependence is what we call cosmic expansion. Galaxies aren't moving through space in the conventional sense. They're being carried along by the evolution of space-time geometry. Let's think about what this means for the question of what the universe is expanding into. In general relativity, space-time is the fundamental arena of physical reality. There's no background space that exists independently of the metric, no pre-existing stage on which space-time performs. The metric is all there is. Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. The metric is all there is. It defines what space and time are. When the metric evolves, when the scale factor grows, space itself is growing. There's no external reference frame needed, no additional dimension for space to expand into, because the metric specifies everything about spatial relationships. This is a deep shift in thinking. In Newton's physics, space was absolute, an unchanging container that existed independently of the objects within it. You could imagine removing all matter and energy in space would still be there, exactly as it was. But in general relativity, space isn't independent of matter and energy. The distribution of mass and energy determines the geometry of space-time, and that geometry is what we call space. Without the metric, there is no space to speak of. So when we ask what the universe is expanding into, we're asking for an external space beyond the metric, a container that holds space-time itself. But general relativity doesn't provide any such thing. The metric is fundamental, and its evolution is a complete description of expansion. There's nothing else needed, nothing else postulated, no additional structure beyond what the equations describe. The universe is the metric, and the metric is expanding, and that's the full story as far as general relativity is concerned. Of course, general relativity might not be the final word. There are hints that at the smallest scales, at the Planck length of about 10 to the minus 35 meters, quantum effects become important and general relativity breaks down. Physicists are working on theories of quantum gravity that might reveal deeper structures underlying space-time. Perhaps space emerges from something more fundamental, some quantum substrate, and perhaps expansion means something different in that deeper description. But even if that's true, it doesn't change the fact that within the framework of general relativity, the framework that describes cosmic expansion with spectacular accuracy, the universe doesn't expand into anything external to itself, which brings us to consider the observational consequences of this framework, the ways we can test these ideas against reality. One of the most powerful aspects of general relativity is that it makes precise, testable predictions. The Friedman equations don't just say the universe can expand, they tell us exactly how the expansion rate should change over time based on what the universe contains. By measuring the expansion rate at different epochs, by looking at how fast the universe was expanding in the past compared to now, we can test whether general relativity correctly describes cosmic dynamics and learn what the universe is made of. The key measurement is the relationship between redshift and distance for galaxies at various distances. Remember, that redshift tells us how much the universe has expanded since light left a galaxy, and distance tells us how far back in time we're looking. By plotting redshift against distance for galaxies spanning a wide range of distances, from nearby to incredibly remote, we can map out the expansion history of the universe. This is one of the great observational programs in cosmology, and it's been carried out with increasing precision over decades. For relatively nearby galaxies, within a few 100 million light-years, the relationship between redshift and distance is linear, exactly as Hubble discovered. But for more distant galaxies, billions of light-years away, deviations from linearity appear. The relationship curves, and the shape of that curve depends on the expansion history. If the universe has been slowing down, as you'd expect if gravity from matter is pulling everything together, the curve bends one way. If expansion has been speeding up, if there's some repulsive force pushing things apart, the curve bends differently. In the late 1990s, two teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, made measurements that shocked the physics community. They used Type 1 as supernova, stellar explosions that can serve as standardized candles because they have a characteristic intrinsic brightness. To measure distances to galaxies billions of light-years away, when they plotted their results comparing supernova distances to redshifts, they found that distant supernovae were fainter than expected. This meant they were farther away than they should be in a universe where expansion was slowing down. The only way to explain the data was to conclude that cosmic expansion is accelerating. The universe isn't just growing, it's growing faster and faster over time. Something is pushing space apart with an ever-increasing vigour, some form of energy that fills all of space and exerts a kind of anti-gravity. This mysterious component is now called dark energy, and it makes up about 68% of the total energy density of the universe. The discovery earned the leaders of both teams the Nobel Prize in Physics in 2011. A recognition of how fundamentally this changed our understanding of the cosmos. Dark energy behaves very differently from matter. While matter's density decreases as the universe expands, because the same amount of matter is spread over larger volume, dark energy's density stays roughly constant. As space grows, more dark energy appears, keeping the energy per unit volume the same. This means that in the early universe, when everything was compressed into a smaller volume, matter dominated. But as the universe expanded and matter density dropped, dark energy became increasingly important. Today, dark energy dominates, and it will continue to dominate into the indefinite future. The simplest explanation for dark energy is that it's the cosmological constant Einstein added to his equations, now interpreted as the energy of empty space itself. Quantum field theory suggests that even vacuum, even empty space, should have energy associated with quantum fluctuations, particles and antiparticles briefly appearing and annihilating. Calculating this vacuum energy from first principles gives a value that's wildly wrong, off by a factor of 10 to the 120th power, perhaps the worst prediction in physics, but phenomenologically a cosmological constant matches the observations well. It's a term in Einstein's equations that acts like an energy density of space itself, causing accelerated expansion. But we have to be honest about what we don't know. We don't understand why the vacuum energy has the value it does, why it's so much smaller than theoretical predictions suggest, or whether it's truly constant or slowly evolving over time. There are alternative theories, modifications of general relativity, exotic energy fields, but none have proven more compelling than the simple cosmological constant. Dark energy remains one of the deepest mysteries in physics, a reminder that even as we measure cosmic expansion with exquisite precision, we still don't understand what's driving it. What these measurements tell us, regardless of the underlying explanation, is that space itself has properties and behaviours that go beyond being an empty container. Space can expand, it can curve, it can have energy density, it can change over time. These aren't properties we'd expect if space were just an inert background. They're properties of a dynamic physical system, something with its own degrees of freedom and evolution. This is what general relativity teaches us, and what observations confirm. Space is a thing, not just an absence of things, and what we call cosmic expansion is the evolution of that thing. And this understanding opens up new questions about the nature of infinity, about whether the universe has an edge, about what exists beyond what we can see, questions we'll explore as our journey continues. Let's return to the question of whether the universe is infinite, because this has profound implications for what expansion means. If space extends forever in all directions, if there are infinitely many galaxies distributed throughout an endless cosmos, then the universe was already infinite at the Big Bang. This sounds paradoxical at first. How can something infinite get bigger? But the paradox dissolves when you think carefully about what infinity means in this context. Imagine an infinite line of evenly spaced markers, extending forever in both directions. Now imagine spacing those markers farther apart, doubling the distance between adjacent markers. You still have infinitely many markers, the line still extends forever, but the density has changed. The average distance between markers has grown. This is analogous to what happens in an expanding infinite universe. Space was infinite in the past, it's infinite now, but the density of galaxies, the average distance between them, has been increasing over time. This means the Big Bang in an infinite universe wasn't the creation of space but the beginning of expansion from an already infinite but extremely dense initial state. Every point in this infinite space was at extreme temperature and density, and expansion began everywhere simultaneously. As time passed, space stretched, densities dropped, and the universe evolved from a hot plasma to the galaxy-filled cosmos we see today. But it was infinite at every moment of this history. Now we have to acknowledge that we don't know for certain whether the universe is infinite. Our observations are limited to the observable universe, the sphere of space from which light has had time to reach us. Beyond that horizon, we simply can't see. Suggest it's either exactly flat, which suggests it's either exactly flat, which would allow for infinity, or so close to flat that we can't measure the deviation. If the universe is finite, it likely has a topology more interesting than simple Euclidean space. It might be shaped like the three-dimensional analogue of a torus, where if you travel far enough in one direction you come back to where you started from another direction. Or it might have some other closed topology, finite in volume but with no boundary or edge. Would reveal a repeating universe, but so would reveal a repeating universe. But so far we've found no convincing evidence for finite topology. What's remarkable is that whether the universe is finite or infinite, expansion doesn't require external space. A finite universe can expand by growing its total volume, becoming larger without needing anything outside itself to grow into. An infinite universe can expand by decreasing its density, increasing distances between objects while remaining infinite in extent. In both cases, expansion is an intrinsic property of the geometry, something that happens within the universe rather than requiring reference to anything beyond. There's something deeply beautiful about the possibility of infinity, something that stretches our intuition and challenges our notion of completeness. If the universe is infinite, then there are infinitely many galaxies, infinitely many stars, infinitely many planets. The sheer scale of existence is beyond anything we can truly comprehend. Every possible configuration of atoms that's consistent with physical law, every possible history, every possible arrangement, occurs somewhere in that infinite expanse. This is both awe-inspiring and humbling, a reminder that we occupy an infinitesimal corner of something vastly larger than ourselves. But infinity also raises puzzles. In an infinite universe that's roughly homogeneous, what does it mean to talk about the total energy? Infinity times any positive density is still infinity. What does it mean for the universe to have begun if it was already infinite at the Big Bang? These questions push against the boundaries of our conceptual frameworks, suggesting that perhaps our usual notions of totality and beginning need refinement when applied to infinite systems. Some physicists argue that infinity is a useful idealization, but not a physical reality, that the universe must be finite even if incredibly vast. Others embrace infinity as a natural outcome of the mathematics, something we should accept even if it strains our intuition. We may never know for certain which is correct, because measuring whether something is infinite versus merely larger than we can observe is fundamentally difficult. But what we can say is that the question of expansion, of what the universe is expanding into, has the same answer in either case. Nothing external, because expansion is an internal property of space-time geometry. Let that thought rest as we shift our attention to the edges of the observable universe, to what we can and cannot see, and why those limitations matter for understanding expansion. Our view of the universe is limited not by the power of our telescopes, but by the finite age of the cosmos and the finite speed of light. There's a fundamental horizon beyond which we cannot see, not because objects there aren't emitting light, but because that light hasn't had time to reach us yet. This horizon is called the cosmic event horizon, or the cosmological horizon, and understanding it helps clarify what expansion means and what questions we can actually answer through observation. Light travels at a finite speed, about 300,000 kilometers per second, and the universe has a finite age, about 13.8 billion years. You might think this means we can see objects up to 13.8 billion light years away, and anything farther is beyond our view. But expansion complicates this calculation. While light was travelling toward us from distant galaxies, space was expanding, carrying those galaxies farther away. The region that emitted light we receive today has been stretched to distances much greater than the light travel time would suggest. Working through the mathematics carefully, taking into account the expansion history of the universe, astronomers calculate that the current size of the observable universe is about 46 billion light-years in radius. This is the come-oving distance to the cosmic horizon, the distance to the most distant objects we can in principle observe. Light from beyond this horizon hasn't had time to reach us yet. Those regions are receding from us faster than light can travel through the expanding space between us. Wait, faster than light? Doesn't that violate relativity? No, and here's why. Special relativity says that nothing can move through space faster than light, that no signal or object can outpace light in the same local region of space-time. But it says nothing about how fast distant regions of space can recede from each other due to expansion. Recession due to expansion isn't motion through space, it's the growth of space itself, and that growth is not limited by the speed of light. Regions sufficiently far away can recede from us faster than light, and there's no violation of relativity in this. In fact, given the current acceleration of cosmic expansion driven by dark energy, there's a more restrictive horizon called the event horizon. This is the boundary beyond which objects are receding so fast that light they emit today will never reach us, no matter how long we wait. Dark energy keeps accelerating expansion, and eventually distant galaxies will be carried away so rapidly that any signal they send in our direction will lose ground, making no progress against the tide of expanding space. Calculations suggest this event horizon is currently about 16 billion light-years away in commoving distance. This means there are galaxies we can see now, galaxies within our current observable universe, that we will never be able to visit or communicate with, even in principle, because they are beyond the event horizon. Their light from the past has reached us, but any signal sent today, even at the speed of light, will never arrive. Expansion will carry them forever beyond our reach. This is a profound kind of cosmic loneliness, a fundamental limit on what regions of the universe we can interact with or learn about. But even this horizon doesn't answer the question of what the universe is expanding into, because the horizon is just a limit on our observation, not a boundary of space itself. Beyond the horizon, space continues. There are galaxies out there, presumably, following the same physical laws, experiencing the same expansion, even though we'll never see them. The universe doesn't end at our horizon any more than the ocean ends at our horizon when we stand on a beach. Our view is limited, but reality extends beyond that limit. Moreover, observers in those distant galaxies have their own horizons, their own observable universes centered on their locations. They see galaxies we can't see, and we see galaxies they can't detect. Each observer has a sphere of observability, and these spheres overlap in some regions and not in others. There's no privileged location, no universal horizon that applies to all observers. Every observer is at the center of their own observable universe, a consequence of the finite speed of light and the finite age of the cosmos. This diversity of perspectives is important for understanding expansion. When we say the universe is expanding, we mean that space between objects is growing everywhere, not just in our local neighborhood. Observers in distant galaxies see the same expansion we do. The same Hubble law, the same relationship between distance and recession speed. Expansion is a global property of space-time, something happening to the geometry as a whole, not a local phenomenon specific to our location. And this global nature of expansion brings us to questions about what exists beyond the observable, about whether our inability to see something means it doesn't exist, about the relationship between reality and observation. One of the most profound questions in cosmology is whether reality is limited to what we can observe, or whether the universe extends beyond our horizon into regions we'll never access. This isn't an idle philosophical question. It has implications for how we think about existence, about scientific knowledge, about what counts as part of the universe. And it connects directly to the question of what expansion means, because if there are regions forever beyond our reach, we might wonder whether they count as part of the same universe or something separate. From a purely operational perspective, science deals with observable phenomena, things we can measure and test. The observable universe is the domain where we can gather data, make predictions, test theories. Everything beyond our horizon is, by definition, inaccessible to direct observation. We can't send signals there or receive signals from there. We can't gather evidence about conditions there or verify that the same physical laws apply. In some sense, the unobservable universe is outside the realm of empirical science, but that doesn't mean it doesn't exist. Our best theories, particularly general relativity and the standard model of cosmology, make predictions that apply everywhere, not just in the regions we can see. If those theories are correct and they've proven remarkably accurate where we can test them, then there's every reason to believe they describe reality beyond our horizon as well. Space continues past the edge of the observable universe. Galaxies form and evolve following the same principles. Stars are born and die. The laws of physics operate without regard for whether we can observe their consequences. This raises interesting questions about what we mean by the universe. Is the universe defined as everything that exists, regardless of whether we can observe it? Or is it more properly defined as the observable universe, the region we have causal contact with? Different cosmologists might answer differently depending on their philosophical inclinations, but most would probably say that the full universe includes everything, observable or not, and that our observations provide a window into a much larger reality. If the universe is infinite, as some evidence suggests it might be, then the vast majority of it is forever unobservable. We see a finite sphere, 46 billion light-years in radius, but if space extends infinitely in all directions, that sphere is an infinitesimally small sample of the whole. This is a humbling thought, that nearly everything that exists is beyond our ability to ever detect or study. We're confined to a tiny bubble of observability within something vastly larger, but even in that tiny bubble, we can learn things about the larger whole. If the universe is homogeneous on large scales, if the same conditions prevail everywhere, then studying our local region tells us about the unobservable regions as well. The cosmic microwave background, for instance, shows that the early universe was extremely uniform, with density variations of only 1 part in 100,000. This suggests that the universe beyond our horizon was in the same hot, dense state we observe in our horizon, subject to the same physics, evolving in the same way. There's also the question of whether unobservable regions can affect us, even if we can't see them directly. In some inflationary models of the early universe, which we'll discuss more later, there might be other regions of space that underwent different amounts of inflation, creating separate bubble universes with potentially different physical constants or laws. These regions would be causally disconnected from us, forever beyond observation, but they might still be part of the same larger space-time. Whether such regions count as part of our universe or as separate universes is partly a matter of definition. What this tells us about expansion is that it's a process happening throughout space, not just in the part we can see. When cosmologists model cosmic expansion, they apply the equations globally to all of space, not just the observable patch. Expansion is a property of the space-time metric, and that metric extends beyond our horizon. The fact that we can't observe distant regions doesn't mean they're not expanding. It just means we can't directly verify that they are. We infer it from our understanding of how space-time behaves according to general relativity. This connects back to our original question in an interesting way. If you ask what the universe is expanding into, and if by quote 10 you mean the entire infinite expanse of space, both observable and unobservable, then the question still has the same answer: nothing external. The metric describing that infinite space is evolving. Distances are growing, but there's no outside, no beyond, no external space for the universe to expand into. The fact that we can only see a small part of it doesn't change the fundamental nature of expansion as an intrinsic property of space-time geometry. Let's allow these ideas about horizons and observability to settle as we move into deeper territory, exploring the very beginning of cosmic expansion and what might have driven it. The standard Big Bang model, with its expanding universe emerging from a hot, dense initial state, explains a tremendous amount about cosmic history. But it left some puzzles unresolved, mysteries about why the universe has the properties we observe. Why is the universe so spatially flat, with geometry so close to Euclidean that we can't measure the deviation? Why is the cosmic microwave background the same temperature in all directions to 1 part in 100,000, even though those distant regions couldn't have been in causal contact to smooth out their temperatures? These were known as the flatness problem and the horizon problem, and they suggested that something important was missing from the story of the early universe. In the early 1980s, physicist Alan Guth proposed a remarkable solution called cosmic inflation. The idea is that in the first tiny fraction of a second after the Big Bang, perhaps around 10 to the minus 36 seconds, the universe underwent a period of exponentially rapid expansion, growing by a factor of at least 10 to the 26th in a minuscule interval of time. This expansion was much faster than the normal expansion we see today, driven by a special energy field in a temporary high-energy state. When that field decayed to its lower energy state, inflation ended, and the energy that had driven it was converted into matter and radiation, reheating the universe and beginning the standard Big Bang expansion we observe. This brief period of inflation solved the flatness and horizon problems elegantly. Any initial curvature of space would have been stretched to near flatness by the enormous expansion, just as the surface of a balloon becomes flatter when you blow it up to enormous size. And regions that were in causal contact before inflation, that had time to smooth out their temperatures, were stretched to sizes larger than the entire observable universe, explaining why we see the same temperature in all directions, even though those regions appear to have never communicated. But inflation does something even more profound. It provides a mechanism for generating the tiny density fluctuations that later grew into galaxies. Quantum fluctuations in the inflaton field, the field driving inflation, were stretched to cosmic scales by the rapid expansion. These quantum variations became classical density perturbations, regions where space had slightly more or less energy than average. After inflation ended, gravity amplified these perturbations over billions of years, turning them into the cosmic web of galaxies and voids we observe today. Everything we see, every structure in the universe, traces back to quantum fluctuations during inflation. The evidence for inflation is circumstantial but compelling. The pattern of temperature fluctuations in the cosmic microwave background matches the predictions of inflationary models with remarkable precision. The spectrum of fluctuations, the way their amplitude varies with scale, is exactly what you'd expect from quantum fluctuations stretched by inflation. The universe's flatness, its large-scale homogeneity, the absence of exotic relic particles that would have been produced in the very early universe, but should have survived if inflation hadn't diluted them away. All of these observations fit naturally into the inflationary picture, but we should be clear about what remains uncertain. We don't know what field drove inflation, what its properties were, or what physics governed its behaviour. There are many different models of inflation, each making slightly different predictions, and we don't yet have enough observational precision to distinguish between them definitively. Some versions of inflation predict the production of gravitational waves that might be detectable in the polarization of the cosmic microwave background, and searches for this signal are ongoing. If found, it would provide strong confirmation of inflation and tell us about the energy scale at which it occurred. Inflation also raises mind-bending questions about the initial conditions. If inflation occurred, it means the entire observable universe, all 46 billion light-years in radius, grew from a region smaller than a proton, a patch of space so tiny that quantum effects dominated. Before inflation, the region that would become our observable universe was microscopically small. And if the universe is infinite, then only an infinitesimal fraction of it underwent the particular inflationary history we observe. Different regions might have inflated by different amounts, or not at all, creating a landscape of bubble universes with different properties. This connects to our question about expansion in an interesting way. During inflation, the universe expanded at a rate far exceeding anything we observe today. Space grew faster than the speed of light by enormous factors. If you're trying to imagine what that expansion looked like from the outside, what the universe was expanding into during inflation, you're making the same category error as before. There was no outside. Inflation was the exponential growth of space itself, an evolution of the metric, happening within the universe rather than requiring external space to expand into, which leads us to consider what might have existed before inflation, before that explosive burst of expansion in the earliest moments of cosmic history. One of the most tantalizing and frustrating questions in cosmology is what happened before the Big Bang, or more precisely, whether there even was a quote 11 general relativity taken to its logical conclusion. Suggests that time itself began at the Big Bang, that there's no earlier moment to speak of. Asking what came before is like asking what's north of the North Pole, a question that assumes a framework that doesn't apply. But this answer feels unsatisfying, and physicists continue to explore whether our understanding of the beginning might be incomplete. The problem is that general relativity breaks down at the very beginning, at the moment of the Big Bang itself. The equations predict a singularity, a point of infinite density and infinite curvature, where the laws of physics as we know them cease to apply. But most physicists don't believe this singularity is physical. They suspect it's a sign that general relativity is inadequate at extreme energies and tiny distances. What's needed is a theory of quantum gravity, a framework that combines general relativity with quantum mechanics and describes how space and time behave when quantum effects are important. Unfortunately, we don't yet have a complete, well-tested theory of quantum gravity. String theory is one candidate, Loop quantum gravity is another, and there are other approaches as well, but none have made predictions we can verify observationally, and none have achieved consensus as the correct description of nature. This means that what happened at the very beginning, in the first tiny fraction of a second when quantum gravity effects should dominate, remains speculative. We can make educated guesses, we can explore mathematical models, but we're honest about the fact that we don't really know. Some models suggest that the Big Bang wasn't the absolute beginning, but a transition from some earlier state. Perhaps the universe underwent a big bounce, contracting from a previous expansion phase and then rebounding into the expansion we observe today. In this scenario, there was a quote 12, a previous cosmic era that collapsed and gave birth to our current universe. The bounce occurred at some minimum size where quantum gravity effects prevented further collapse, turning contraction into expansion without ever reaching a true singularity. Other models propose that time is emergent, that it doesn't extend infinitely into the past, but has a beginning without requiring a singularity. In this view, you can trace cosmic history back to earlier and earlier moments, but there's a first moment, a beginning of time itself, and asking what came before is meaningless, because there is no temporal structure before that point. Time, like space, is a property of the universe that emerged from some more fundamental quantum state. There are also multiverse scenarios where our Big Bang was a local event in a larger eternal structure. Perhaps there's a vast inflating space where bubble universes like ours are constantly nucleating, each with its own Big Bang, its own expansion history, its own physical constants. In this picture, our universe had a beginning, but the larger multiverse is eternal, existing for infinite time with no overall beginning. The question of ultimate origins is pushed back from our universe to this larger structure, but it remains unanswered. What's fascinating and perhaps frustrating about all these scenarios is that they may be untestable. If time truly began at the Big Bang, we can't gather evidence from before because there is no before. If there was a prior state, its information might have been erased by the violent conditions of the Big Bang or inflation, leaving no observable trace. The earliest moments we can potentially probe observationally are from after inflation ended, when the universe was already macroscopic and classical. Everything before that is inference and theory, extrapolation based on our understanding of physics, but not directly observable. This brings us to an important realization about the limits of science. There are questions we might never be able to answer definitively through observation and experiment. The absolute origin of the universe, what existed before the Big Bang if anything, why there's something rather than nothing, these might remain forever in the realm of philosophy and speculation, rather than empirical science. This doesn't mean they're not worth contemplating, but it does mean we should be humble about the certainty of our conclusions. For our purposes, thinking about what the universe is expanding into, the key insight is that whether time had a beginning or extends infinitely into the past, whether there was a before or not, expansion remains an intrinsic property of space-time. Even if the universe emerged from some prior state, that emergence was still the evolution of a metric, the growth of space itself. Not expansion into a pre-existing void. The question dissolves regardless of the ultimate origin story. Let's carry this sense of humility and wonder forward as we explore what drives the expansion we observe today. We've mentioned dark energy several times, this mysterious component that makes up the majority of the universe's energy density and drives the accelerating expansion we observe today. But it's worth dwelling on just how strange and poorly understood dark energy really is, how it challenges our intuitions and reveals gaps in our knowledge. Understanding dark energy is crucial, not just for predicting the future of cosmic expansion, but for grasping what space itself might be. The simplest model of dark energy is the cosmological constant, a term in Einstein's equations that acts like an energy density of empty space itself. If the vacuum has energy, if even empty space in its lowest energy state has a non-zero energy density, then that energy contributes to cosmic expansion. Unlike matter, which dilutes as the universe expands because the same mass is spread over larger volume, vacuum energy has constant density. As space grows, more vacuum energy appears, keeping the energy per unit volume fixed. This leads to accelerated expansion because the gravitational effect of dark energy is repulsive rather than attractive. Has quantum mechanical properties, has negative pressure, a kind of tension that causes space itself to push apart. The more dark energy there is, the stronger this repulsion, and since dark energy density stays constant while matter density decreases, dark energy becomes increasingly dominant over time, leading to ever faster expansion. The value of the cosmological constant, if that's what dark energy is tiny by particle physics standards, but huge in its cumulative effect. It corresponds to an energy density of about 6 times 10 to the minus 10 joules per cubic meter, a minuscule amount in any small region but enormous when multiplied by the volume of the observable universe. This energy is causing the universe to expand at an accelerating rate, doubling in size every 10 billion years or so, and this acceleration will continue indefinitely into the future if dark energy remains constant. But here's the puzzle that keeps physicists awake at night. When you try to calculate the vacuum energy from quantum field theory, taking into account the zero-point energies of quantum fields, the value you get is absurdly large, about 120 orders of magnitude larger than what we observe. This is the cosmological constant problem, arguably the biggest mismatch between theory and observation in all of physics. We don't understand why the vacuum energy is so much smaller than it should be, or what mechanism is cancelling out the enormous contributions that quantum theory predicts. Some physicists think this suggests we're missing something fundamental about how quantum field theory works, or that there's new physics at play that precisely cancels most of the vacuum energy. Others speculate that the observed value is set by anthropic selection, that universes with larger cosmological constants expand too rapidly for galaxies to form and life to emerge, so we find ourselves in a universe with a small value simply because we couldn't exist otherwise. This anthropic explanation feels unsatisfying to many, but it might be the correct answer in a multiverse where different regions have different cosmological constants. There's also the possibility that dark energy isn't a cosmological constant but something more dynamic, a field that evolves over time. This is called quintessence, and there are many models where a scalar field slowly rolls down a potential energy curve, changing its energy density gradually over cosmic history. In these models, dark energy could strengthen or weaken in the future, or it could even reverse sign, turning from repulsive to attractive and causing the universe to eventually recollapse. We don't have strong observational evidence for quintessence over a simple cosmological constant, but it remains a possibility that ongoing surveys are testing. What dark energy tells us about expansion is that space itself can have energy, can exert pressure, can drive cosmic dynamics. This is a remarkable property, far removed from the empty passive container we might have imagined space to be. Space is an active participant in the universe's evolution, something with its own properties and behaviours, something that can push itself apart with increasing vigour. This makes the question, quote, 13 even more pointed, because we're not talking about a passive background, but an active physical system with energy and dynamics, and yet the answer remains the same. Dark energy is energy of space itself, not energy in space, and its effects are intrinsic to the geometry. When dark energy causes space to expand, it's not pushing space into something external, it's evolving the metric, changing the geometry from within. There's no outside, no beyond, just the continuous evolution of space-time governed by Einstein's equations, with a cosmological constant or quintessence field included. This understanding leads us to contemplate the deep connection between space and energy, between geometry and physics, a connection we'll explore further as we continue. To truly appreciate why the universe doesn't expand into anything, We need to think carefully about what general relativity tells us about the nature of space and time. Einstein's great insight was that space-time isn't a rigid background, but a flexible dynamic structure that responds to the presence of matter and energy. Mass and energy curve space-time, and that curvature is what we experience as gravity. The Earth orbits the Sun not because it's pulled by a force acting through empty space, but because the Sun's mass curves the space-time around it, and the Earth follows a geodesic, a straightest possible path through that curved geometry. This curvature is real and measurable. Light passing near the Sun is deflected by the curvature of space-time, an effect first observed during a solar eclipse in 1919 and now measured routinely. Gravitational time dilation, the slowing of clocks in strong gravitational fields, is measured with atomic clocks and must be accounted for in GPS satellites to maintain accuracy. Gravitational waves, ripples in space-time produced by accelerating masses, have been directly detected by LIGO and other observatories, confirming that space-time can oscillate and propagate disturbances. Space-time isn't just a mathematical description, it's a physical entity with measurable properties. When we say space is expanding, we mean that the metric, the mathematical object that defines distances in space-time, is evolving. In an expanding universe, the distance between two stationary points grows over time. If you imagine a grid of points all at rest relative to the cosmic expansion, not moving through space but just sitting still, the distance between adjacent grid points increases as time passes. This is expansion, the growth of distances defined by the metric, and it happens without the points moving through space in the conventional sense. This distinction between expansion of space and motion through space is crucial. When a galaxy moves through space, when it has a peculiar velocity relative to the cosmic expansion, it's actually moving, changing its position in a way that requires energy and momentum. But recession due to expansion isn't motion in this sense. Galaxies at rest with respect to cosmic expansion aren't moving through space. They're being carried along by the evolution of space-time geometry. No energy is required for this recession. No momentum is exchanged. It's simply the metric changing. You might wonder how we can tell the difference between a galaxy moving through space and space expanding to carry the galaxy away. The answer lies in the pattern of recession velocities. Motion through space would produce random velocities, some galaxies approaching, some receding, with no particular correlation with distance. But expansion produces the Hubble law. Recession speed proportional to distance, a pattern that's the same from every observer's perspective. This regularity is the signature of expansion rather than motion. The flexibility of space-time, its ability to curve and stretch, means that geometry is not fixed but dynamic. The angles of triangles, the ratios of circumferences to diameters, the rate at which clocks tick. All of these can vary from place to place and change over time depending on the distribution and motion of matter and energy. Space-time is a physical field, as real as the electromagnetic field or any other field in physics, and it has dynamics governed by Einstein's equations. When we study cosmic expansion, we're studying the evolution of this field on the largest scales. This brings us to a profound realization. If space-time is a physical field, if it's the fundamental structure that defines what we mean by space and time, then asking what it's expanding into is asking what a field expands into. But fields don't expand into anything external to themselves. A field occupies space, but if the field is space, if the metric field is what defines spatial relationships, then the field's evolution is self-contained. There's no external arena needed because the field is the arena. This might seem like philosophical word games, but it's deeply physical. General relativity makes precise predictions about how the metric evolves based on energy and matter content, and those predictions match observations exquisitely. The framework doesn't require or postulate any structure beyond the metric. If you add extra structure, if you imagine a background space that the metric lives in, you're adding something that doesn't appear in the theory and isn't needed to explain what we see. It's an unnecessary metaphysical addition. So when cosmologists say space is expanding, they mean the metric is evolving in a particular way. Distances are growing, and this evolution is a complete description. Asking what it's expanding into is asking for something beyond the metric, but the metric is all there is. Space is the metric, and the metric is changing, and that's the full story as far as general relativity and observations can tell us. Let these ideas about the physical reality of space-time settle as we move toward contemplating what expansion means for the future of the cosmos. Geometry, the study of shapes and spaces and their properties, has been part of human thought for thousands of years. Euclid codified the geometry of flat space, where parallel lines never meet, and the angles of triangles sum to exactly 180 degrees. For millennia, this seemed like the only geometry, the necessary structure of space itself, as inevitable as logic. But in the 19th century, mathematicians discovered that other geometries are possible. Spaces where parallel lines converge or diverge, where triangles have different angle sums, geometries that are just as mathematically consistent as Euclid's but describe different kinds of space. These non-Euclidean geometries were initially explored as pure mathematics, abstract systems with no obvious connection to physical reality, but Einstein realised they're exactly what's needed to describe gravity. Space-time isn't flat in Euclid's sense when mass is present, it's curved, and the curvature is what we feel as gravity. The geometry of space-time is dynamic and variable, determined by the distribution of matter and energy through Einstein's field equations. This was a revolutionary idea, that geometry isn't an unchanging framework, but a physical property that responds to physical conditions. On cosmic scales, when we talk about the geometry of the universe, we mean the large-scale curvature of space. There are three main possibilities. The universe could be positively curved, like the surface of a sphere, where parallel lines eventually meet, and triangles have angles summing to more than 180 degrees. Such a universe would be finite in volume, shaped like the three-dimensional analogue of a sphere's surface, and would eventually recollapse if not for dark energy. Or the universe could be negatively curved, like a saddle shape, where parallel lines diverge and triangles have angles summing to less than 180 degrees. This geometry extends infinitely, and would expand forever even without dark energy. The third possibility is that the universe is flat, exactly Euclidean on large scales, and this is what observations suggest. Measurements of the cosmic microwave background, particularly the pattern of hot and cold spots and their angular sizes, are sensitive to curvature. If space were positively curved, those spots would appear larger than expected. If negatively curved, they'd appear smaller. What we observe is that they're exactly the size predicted for flat geometry, within measurement uncertainty. This flatness is one of the great puzzles inflation was designed to explain, because it requires an incredibly precise balance of energy density in the early universe. A flat universe can be either infinite or finite depending on its topology. The global structure of how space connects to itself. The simplest flat geometry is infinite Euclidean space extending forever in all directions. But you can also have flat spaces that are finite, like a 3 torus where space wraps around on itself. If you travelled far enough in any direction, you'd come back to where you started from another direction, but locally the geometry would still be flat. Searchers for this kind of cosmic topology look for repeated patterns in the distribution of galaxies or the cosmic microwave background, but so far we've found no convincing evidence. What does geometry tell us about expansion, and what the universe is expanding into? Everything, really. Expansion is a property of the geometry, a time evolution of the metric, in a flat universe. The metric can be written in a particularly simple form where space is divided by a scale factor that grows over time. As the scale factor increases, distances between stationary points grow proportionally. This is expansion, described entirely in terms of the geometry's evolution, with no reference to external space. In a positively curved universe, expansion means the radius of curvature is growing, the three-dimensional analogue of a balloon inflating. Is intrinsic, measurable by doing geometry is intrinsic, measurable by doing geometry within the space, and its growth is similarly intrinsic. In a negatively curved universe, expansion dilutes the curvature, making space locally flatter over time. But again, this is an evolution of internal geometry. The mathematics of general relativity handles all of this without ever invoking space outside the universe. The field equations relate the geometry, curvature, expansion rate, to the energy content, matter, radiation, dark energy. And that's a closed system. You can solve for how the metric evolves given the energy content, or conversely figure out what energy is present based on how the metric behaves. There's no term in the equations for quote 1,4 quote or quote 1,5 quote, because no such concept is needed. This is why physicists keep saying the universe isn't expanding into anything. It's not evasiveness or inability to explain. It's that the mathematical framework describing expansion is complete without such a concept. Adding the idea of external space would be like adding epicycles to planetary orbits after we've explained their motion with gravity. It's extra structure that doesn't appear in the theory, doesn't match observations, and doesn't make predictions. It's a vestige of trying to understand expansion through everyday analogies rather than through the actual physics. And this understanding of geometry as physical reality, not just mathematical description, leads us gently toward contemplating the implications for our existence within this expanding universe. Having explored the physics and mathematics of cosmic expansion, let's bring the focus back to something more human, our place within this vast and growing universe. We exist in a small corner of space, on a rocky planet orbiting an ordinary star, in a galaxy that's one of hundreds of billions, and the space around us is stretching, carrying distant galaxies ever farther away. What does this expansion mean for us? How does it shape the cosmos we inhabit and the future we face? One thing to understand is that expansion happens only on the larger scales, between galaxies and clusters of galaxies that aren't gravitationally bound to each other. On smaller scales, where gravity is strong enough to hold things together, expansion is irrelevant. The Earth isn't expanding, the solar system isn't expanding, even our Milky Way galaxy isn't expanding. Gravity keeps these structures bound, and the local space-time curvature from mass prevents the expansion from tearing them apart. It's only when you look at distances of hundreds of millions of light years, and beyond that, expansion dominates over local gravitational attraction. This means our everyday life is completely unaffected by cosmic expansion. The space in your room isn't growing, atoms aren't getting farther apart, your body isn't expanding. The forces that hold matter together, electromagnetic forces binding atoms into molecules and molecules into structures, are vastly stronger than the gentle tug of cosmic expansion. You'd never notice expansion through local measurements. Only by looking at distant galaxies and measuring their recession can we detect it. Even the Milky Way and our nearest large neighbour, the Andromeda Galaxy, aren't receding from each other despite cosmic expansion. They're part of the same gravitationally bound structure called the local group, and in fact they're actually moving toward each other, destined to collide and merge in about 4 billion years. This local motion through space, called peculiar velocity, can overcome expansion when objects are close enough that gravity matters. It's only at larger distances between separate clusters and superclusters that expansion wins out and recession dominates. But expansion does shape the universe we can see and will see in the future. Because space is stretching, light from distant galaxies is red-shifted, stretched to longer wavelengths. The most distant galaxies we can currently detect are so far away that their light has been stretched from visible wavelengths into the infrared, requiring specialized telescopes like James Webb to observe them. As we look at more and more distant galaxies, we see them as they were farther and farther back in time, because their light has been travelling for longer. The observable universe is like a time machine, showing us the history of cosmic evolution. This redshift has another consequence. Distant galaxies appear dimmer than they would in a non-expanding universe. Not only because they're far away, but because their light has lost energy to expansion. Each photon is stretched to longer wavelength, reducing its energy, and the rate at which photons arrive is also reduced because space between emission and reception has grown. This makes observing the most distant galaxies challenging, requiring long exposure times and sensitive detectors. There's something poignant about the fact that expansion is carrying most of the universe away from us, into regions we can never reach. The galaxies we see today in the most distant parts of the observable universe are already far beyond the cosmic event horizon, receding so fast that any signal we send toward them, even at the speed of light, will never arrive. We can see their past, the light they emitted billions of years ago. But we can never communicate with them or visit them. They're forever beyond our grasp, isolated from us by the expansion of space. This cosmic isolation will only deepen over time. As dark energy continues to accelerate expansion, more and more galaxies will cross beyond the event horizon, disappearing from our view as their light becomes too redshifted to detect and new light they emit fails to make progress against expanding space. Billions of years from now, observers in the 90 minutes, you've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. Billions of years from now, observers in the Milky Way will see a much emptier universe, with only the galaxies of our local group visible, everything else having been carried beyond the horizon. The universe will appear static and empty, the evidence for the Big Bang and expansion fading into obscurity. This realization that we live in a privileged epoch when the full extent of cosmic history is still visible is humbling. We're lucky to exist at a time when we can observe the cosmic microwave background, measure the expansion rate, see distant galaxies as they were in the early universe. Future civilizations, if they arise, might not have access to this evidence unless our generation preserves the knowledge we've gained. The universe is teaching us its history now, but it won't keep the textbook open forever. Let's carry this sense of our cosmic context forward as we explore what expansion reveals about the nature of time itself. Time is one of the most familiar yet mysterious aspects of our experience. We feel its passage constantly. We measure it with clocks. We organise our lives around it. Yet explaining what time actually is and why it flows in one direction remains one of physics' deepest challenges. Cosmic expansion offers some insight into these questions, connecting the arrow of time we experience to the evolution of the universe as a whole. In the fundamental laws of physics, time appears to be symmetric. Most equations work just as well running forward as backward. Describing a movie that could play in reverse without violating physical principles, and yet our experience of time is deeply asymmetric. We remember the past, but not the future. Eggs break, but don't unbreak. Heat flows from hot to cold, but not the reverse. This asymmetry, the arrow of time, demands explanation. Why does time have a direction when the fundamental laws seem not to? The answer, most physicists believe, lies in entropy, the measure of disorder, or the number of ways a system can be arranged microscopically while looking the same macroscopically. The second law of thermodynamics says that entropy tends to increase in isolated systems, disorder tends to grow, and this increase defines the direction of time's arrow. The past is the direction of lower entropy, the future is the direction of higher entropy, and time flows from one to the other because low entropy configurations naturally evolve toward high entropy ones. But this raises a puzzle. If entropy always increases, the universe must have started in an extremely low entropy state. highly ordered, improbably organized. The Big Bang was such a state with matter and energy distributed almost perfectly smoothly, with only tiny fluctuations. As the universe expanded and evolved, entropy increased. Matter clumped into stars and galaxies, creating local order but increasing overall disorder. Stars burned, converting organized nuclear fuel into diffuse radiation, increasing entropy further. Everything we observe is consistent with the universe starting in low entropy and evolving toward higher entropy as time progresses. Cosmic expansion itself is connected to this entropy increase. As space grows, as energy spreads over larger volumes, as radiation is stretched to longer wavelengths and lower temperatures, the universe becomes more disordered in a certain sense. The expansion provides a one-way direction to cosmic evolution, from the dense, hot, smooth early universe to the cool, dilute, structured late universe. This cosmological arrow of time aligns with the thermodynamic arrow, both pointing in the same direction, from past to future. Some physicists speculate that the arrow of time is entirely due to the special initial conditions of the Big Bang, that if the universe had started in a high entropy state instead, time wouldn't have a direction. In such a universe, nothing interesting would happen. There would be no evolution, no structure formation, no memory, no causality as we understand it. The fact that we exist to contemplate time's arrow means we must find ourselves in a universe with low entropy initial conditions, where time flows and change occurs. But why were the initial conditions so special? Why did the universe begin in low entropy rather than high? This is one of cosmology's deepest questions, and we don't have a fully satisfactory answer. Inflation provides part of the story, explaining how the universe could have been smoothed to such uniformity. But it doesn't explain why the inflaton field started in the right state to drive inflation. Perhaps the answer involves quantum gravity and the birth of the universe from a more fundamental state, or perhaps it's anthropic, that we observe low entropy beginnings because we couldn't exist otherwise. What expansion tells us about time is that time is not separate from the evolution of the universe, but deeply connected to it. The flow of time, the increase of entropy, the growth of space, these are all aspects of the same cosmic evolution. Time has a direction because the universe is changing, expanding, evolving, and that evolution is irreversible. You can't unexpand the universe any more than you can unbreak an egg. Both are processes that increase entropy and define time's forward direction. This also connects to our question about what the universe is expanding into. Time is not an external parameter that exists independently of the universe, flowing whether anything happens or not. Time is the dimension along which the universe evolves, part of space-time itself. Asking what existed before time began is like asking what's expanding into. It presumes a framework that doesn't apply. Time and space are both properties of the universe, both described by the metric, both emerging from the same fundamental reality. As we contemplate time's nature and its connection to cosmic expansion, we're led to consider the ultimate fate of this expansion, where it's all heading, what the far future holds. If cosmic expansion continues, if dark energy persists in driving space apart at an accelerating rate, what does the far future hold? This is a question cosmologists can address with some confidence, because the dynamics are well understood, even if the fundamental nature of dark energy remains mysterious. The picture that emerges is one of increasing isolation, cooling, and eventual quiescence, a universe growing ever larger, darker, and emptier over timescales that dwarf the current age of the cosmos. In the near term, cosmically speaking, the next few tens of billions of years, the universe will continue to look much as it does now. Galaxies will keep forming stars, though the rate will decline as gas supplies are exhausted. Clusters of galaxies will remain gravitationally bound, their internal motions preventing expansion from pulling them apart. our local group will merge into a single large galaxy as Milky Way and Andromeda collide. For observers within gravitationally bound structures, daily life, if we can call cosmic processes that, will continue relatively normally. But beyond the local group, more and more galaxies will fade from view as they're carried beyond the cosmic event horizon. The universe will appear to empty out, with only nearby structures visible. In 100 billion years, an observer in our merged galaxy would see an island universe, a single large galaxy surrounded by darkness, with no evidence of the broader cosmos beyond. The cosmic microwave background would be so redshifted that it would be undetectable. The expansion rate would be impossible to measure because there would be no receding galaxies to observe. All evidence for the Big Bang and cosmic evolution would have vanished. This raises a sobering thought. If we existed in that far future rather than now, we might never discover the truth about cosmic origins. The universe would appear static and eternal, containing only our local galaxy and nothing else. This is why cosmologists sometimes speak of our current epoch as a golden age for cosmology, when the evidence is still available to piece together cosmic history. We're fortunate to live when we do. Continuing into the even more distant future, trillions of years from now, star formation will cease entirely as the universe runs out of hydrogen gas. Existing stars will age and die. White dwarfs cooling into black dwarfs, neutron stars radiating away their energy, black holes accreting the last remaining matter. The universe will enter what's called the degenerate era, where stellar remnants dominate and no new stars are born. Galaxies will become dark, haunted by the fading embers of once bright stars. After 10 to the 14 years, 100 trillion years, even these stellar remnants will have mostly evaporated or been swallowed by black holes. Galaxies will dissolve as stars are ejected through gravitational interactions or fall into central black holes. The universe will enter the black hole era, dominated by black holes of various masses slowly evaporating through Hawking radiation, a quantum process where black holes lose mass by radiating particles. This evaporation is incredibly slow, with stellar mass black holes taking 10 to the 66 years to evaporate, and supermassive black holes taking vastly longer. Eventually, after unimaginable stretches of time, even the largest black holes will evaporate, leaving a universe filled only with a thin gas of elementary particles, photons and neutrinos, all separated by vast distances and cooled to temperatures infinitesimally above absolute zero. This is the heat death, the maximum entropy state where no usable energy remains, no structure persists, nothing changes. The universe will be dark, cold, and essentially dead, expanding forever with nothing interesting happening anywhere, or maybe not. There are speculative ideas about how life or structure might persist even in this far future. Exotic forms of computation running on black hole evaporation, civilizations that adapt to ever lower temperatures, processes we haven't imagined that might sustain complexity. And there are alternative scenarios where dark energy doesn't remain constant but decays or reverses, where the universe might eventually stop expanding and recollapse, or where new physics emerges at late times to change the trajectory. But based on what we currently observe and understand, the most likely future is one of eternal expansion, accelerating eternally due to dark energy, leading eventually to a cold, dark, empty cosmos, where the brief era of galaxies and stars and planets will be remembered, if at all, only by the faint traces they left behind. This is not a comforting vision, but it's an honest one based on the best science we have. What does this tell us about expansion and what it's expanding into? Even in this far future, even when the universe is vastly larger and older than it is now, expansion will still be an evolution of the metric, an internal property of space-time. The answer to what is expanding into will be the same then as it is now. Nothing external, because expansion is self-contained within the geometry of space-time itself. Let these thoughts about deep time and distant futures rest gently as we turn to questions of how we think about expansion, how language shapes and sometimes misleads our understanding. Throughout this exploration, we've been wrestling with language, trying to use everyday words to describe phenomena that lie far outside everyday experience. Quote 17 is one such word, loaded with connotations from how we use it in daily life, and those connotations can mislead us when we apply the word to cosmic phenomena. Let's think carefully about how language shapes our understanding and where it leads us astray. When we hear the universe is expanding, we reflexively apply the grammar of expansion we know from experience. Something expands into something else. A balloon expands into air. A city expands into countryside. An expanding object grows by occupying space that was previously occupied by something else, or at least by empty space that was there beforehand. This grammatical structure, subject expands into object, seems fundamental to what expansion means linguistically. But cosmic expansion doesn't fit this grammar. There's no object, no into, because space isn't expanding into anything external. The language fails because it's built on experiences that don't apply to the universe as a whole. We've never experienced anything expanding without an external reference frame, so our language doesn't have a natural way to express that concept. We're forced to say things like, space expands into nothing, or space expands into itself. Phrases that sound contradictory or meaningless, because they violate the grammatical expectations the word expand creates. This is a general problem in physics. Many concepts are difficult to describe in everyday language because they involve phenomena we never encounter directly. Quantum superposition, curved space-time, fields permeating space. These don't have direct analogues in daily experience, so we use metaphors and analogies and mathematical descriptions, always aware that the everyday words are imperfect. The map is not the territory, and linguistic descriptions are maps that sometimes distort the territory they're meant to represent. Perhaps we should use different language for cosmic expansion. Instead of saying space expands, we could say space evolves, or the metric grows, or distances increase. These phrasings avoid some of the misleading connotations of expand, but they have their own issues. Evolve is vague. Metric grows requires understanding what a metric is. Distances increase sounds like it might be about objects moving. There's no perfect terminology because we're describing something genuinely outside common experience. Physicists resort to mathematics for precisely this reason. Equations don't have the baggage of everyday language. When you write down the Friedman equations describing how the scale factor of the universe changes over time, there's no ambiguity about what's expanding into what. The mathematics is clear and precise, and it doesn't require the concept of external space. This is why physicists sometimes seem evasive when asked what the universe is expanding into. They're struggling to translate mathematical clarity into linguistic terms that inevitably distort the meaning. But most people don't think in mathematical equations. They think in words and concepts and mental images. So we use analogies, the raisin bread, the balloon surface, the stretching rubber sheet. These are teaching tools meant to convey aspects of the truth while acknowledging they're imperfect. The balloon surface analogy helps convey that expansion doesn't require external space, but it introduces the misleading idea of curvature in an extra dimension. The raisin bread helps show how all raisins recede from all others, but it suggests there's dough between the raisins when really there's just space. Every analogy illuminates some aspects while obscuring others. Maybe the real lesson is humility about language's limits. Words are tools evolved for describing the middle-sized world of everyday objects at moderate speeds and energies. When we apply them to the very large, the very small, the very fast, they strain and sometimes break. We can stretch language to encompass new concepts. We can invent new terminology, but we should always remember that the words are approximations, pointers toward mathematical structures that capture the reality more faithfully. This applies to underscore, underscore, quote, underscore 27, underscore, underscore as well, the word we've used repeatedly to answer what the universe expands into. What does nothing mean in this context? It doesn't mean a void or empty space, because those are still something spatial structures. It means the absence of any external space or structure beyond the metric describing our universe. But quote 29 quote carries connotations of emptiness and absence that might mislead, suggesting there's a void out there when really there's no quote 30 quote at all. Perhaps we should say the question is malformed, rather than that the answer is nothing. But even that phrasing has problems. The point isn't that we should stop using language to discuss cosmology. Obviously, we must communicate somehow. The point is awareness that language is imperfect, that words carry baggage from everyday use that may not apply to cosmic phenomena, and that when our intuitions clash with physics, it might be the language creating the clash rather than the physics being contradictory. As we carry these reflections forward, let's consider what this means for how we understand reality itself, for what it means to know something about the universe. Science is built on observation and experiment, on gathering evidence from the world and testing hypotheses against that evidence. But cosmic expansion raises interesting questions about the limits of observation and what it means to know something we cannot directly see. We can't observe space itself expanding. We can only infer it from the recession of galaxies. We can't travel to the edge of the observable universe to check if expansion continues beyond. We can't run controlled experiments on the universe as a whole. So what does it mean to say we know the universe is expanding? And how certain can we be about something so removed from direct experience? The evidence for expansion is indirect but compelling. We see galaxies receding with speeds proportional to distance, exactly as predicted if space itself is growing. We detect the cosmic microwave background, light from the early universe stretched by expansion to microwave wavelengths. We observe light elements in the ratios predicted by Big Bang nucleosynthesis, the formation of hydrogen and helium in the early hot universe. We measure the changing expansion rate over cosmic history, using supernovae and other distance indicators. All of these observations fit together into a coherent picture described by general relativity and the standard cosmological model. This convergence of evidence from multiple independent sources is what gives cosmologists confidence. It's not that any single observation proves expansion beyond doubt. It's that many different observations, using different techniques and probing different aspects of cosmic history, all point to the same conclusion. Explains phenomena across vast ranges of scale and time, we can be reasonably confident we're onto something true about reality. But there are limits to what we can know. We can't observe beyond the cosmic horizon, so we can't directly verify that expansion continues in regions we'll never see. We can't test our theories in regimes vastly different from those we can access, so we extrapolate and hope the same laws apply. We can't run the universe multiple times to see if the same patterns emerge, so we rely on the assumption that the laws of physics are universal and don't vary with location. These are reasonable assumptions supported by what we can test. But they remain assumptions. This is where theoretical physics plays a crucial role. General relativity isn't just a descriptive model that summarizes observations, it's a theoretical framework that makes predictions, that tells us what should happen in regimes we haven't observed yet. When we apply general relativity to the universe as a whole, it predicts expansion or contraction. It tells us how the expansion rate should change based on energy content. It describes what happens at the Big Bang. We test these predictions where we can, and when they match observations, we gain confidence that the theory is correct even in untested regimes. The question, what is the universe expanding into, touches on this issue of knowability. If the answer is that there's nothing external, that expansion is self-contained within space-time, how can we be sure? We can't observe this nothing. We can't detect the absence of external space. We conclude it's not there because the theory doesn't require it, and observations don't indicate it. But is that the same as knowing it doesn't exist? This gets into philosophical questions about what existence means and what standards of proof are appropriate. One position is instrumentalism, that scientific theories are tools for predicting observations, and questions about what's really happening beyond what we can observe are meaningless, or at least unscientific. From this perspective, the question of what the universe expands into has no answer, because it asks about something unobservable in principle. The only meaningful statements are about what we can measure, and we can measure recession velocities, redshifts, the expansion rate, but not any external space. Another position is scientific realism, that our best theories are approximately true descriptions of reality, including aspects we can't directly observe. From this perspective, general relativity tells us that space is the metric, and the metric doesn't require or predict external space, so there isn't any. This is as close to knowing as we can get in science. Being confident based on theoretical understanding and all available evidence, even though direct observation is impossible. Most physicists probably fall somewhere between these extremes, being pragmatic about what can be known while maintaining confidence that well-tested theories reveal truths about reality. The key is honesty about uncertainty. Acknowledgement of what we know well versus what we're inferring versus what's pure speculation. Cosmic expansion is extremely well established by multiple lines of evidence. The theoretical framework describing it, general relativity, is one of the most thoroughly tested theories in physics. The conclusion that expansion doesn't require external space follows naturally from that framework. But ultimate certainty, final proof, those remain forever elusive. What we can say with confidence is that the universe behaves as if space itself is expanding, as if expansion is an intrinsic property of space-time geometry, requiring no external space. This behaviour matches observations and predictions to extraordinary precision. Whether there's some deeper reality beyond this description, some additional structure we haven't detected, remains possible, but unsupported by evidence. Science proceeds by building on what we can observe and test, and by that standard, cosmic expansion into nothing external is as well established as any fundamental truth about the cosmos. Let these reflections on knowledge and observation settle as we begin moving toward the more philosophical and contemplative territory that awaits in the final chapters of our journey. We've covered a lot of ground in this exploration, from the observational evidence for expansion to the theoretical framework describing it, from the Big Bang's beginning to the universe's far future. But for all we've learned, enormous mysteries remain. We don't understand dark energy, the dominant component of the universe driving accelerated expansion. We don't know what happened at the absolute beginning, whether time had a start or extends infinitely into the past. We don't know if the universe is finite or infinite, whether there are other universes beyond our horizon, whether our physical laws are universal or just local peculiarities. And we're still grappling with what it means for space to expand without expanding into anything. There's a temptation in science communication to present knowledge as more complete and certain than it really is, to give neat answers that close off questions rather than opening them up. But I think there's something valuable, even necessary, in acknowledging how much we don't know, in sitting with uncertainty and being honest about the limits of human understanding. Not knowing isn't a failure. It's the current state of an ongoing investigation into the deepest questions we can ask about reality. The history of science is full of questions that once seemed unanswerable, becoming answerable as new tools and insights emerged. The nature of stars, the age of the Earth, the structure of atoms, the origin of species, all were mysteries that science eventually illuminated. But it's also full of questions that led to even deeper questions, answers that revealed new puzzles, understanding that showed us how much we didn't understand. Knowledge doesn't just fill in gaps, it often reveals that the gaps are larger and stranger than we imagined. Cosmic expansion is like that. We've answered some questions definitively. Yes, the universe is expanding. Yes, it had a hot, dense beginning. Yes, expansion is accelerating. But answering those questions opened up new ones. What is dark energy? Why was the initial entropy so low? What is the ultimate fate of expansion? And the question we've been circling, what is space itself really? And what does it mean for it to expand without needing external space? Remains philosophically puzzling even as we've developed a mathematical framework to describe it. I find something beautiful in this ongoing mystery, in the fact that reality is deeper and stranger than we can fully grasp with our current understanding. It would be disappointing if the universe was simple, if we'd figured everything out, if there were no more surprises waiting. The persistent mysteries, the questions that resist easy answers, these are invitations to keep thinking, keep observing, keep trying to understand. They're what makes science an ongoing adventure rather than a completed project. There's also humility in not knowing. We're small beings on a small planet, and we've only been doing systematic science for a few centuries. The universe is nearly 14 billion years old and extends to distances we can barely conceive. The fact that we've learned as much as we have is remarkable, but it would be hubris to think we've penetrated all the way to final truth. Reality doesn't owe us the courtesy of being comprehensible. The fact that we can understand anything at all is a gift. This humility extends to being honest about when our language and concepts break down, when we're pushing up against the limits of what words can express and minds can visualize. The question, what is the universe expanding into, might be one of those cases where our intuition, built on everyday experience, leads us astray. The universe doesn't conform to our expectations. It simply is what it is, and our job is to observe carefully, think clearly, and accept that sometimes the answer to a question is that the question itself was based on faulty assumptions. But even saying that doesn't fully dissolve the sense of puzzle, does it? There's still something almost impossible to grasp about space expanding without expanding into anything, about the universe being all there is with nothing beyond. Our minds rebel against it, because we're so used to thinking of things as embedded in larger contexts. Every object is in a room, every room is in a building, every building is on Earth, Earth is in the solar system in galaxy, galaxy in universe. Saying the universe isn't in anything, that there's no next level, violates this pattern we use to make sense of the world. Perhaps the lesson is that some aspects of reality are genuinely beyond full intuitive grasp, that we can understand them mathematically and verify them observationally without being able to visualize them in the way we visualize everyday objects. And perhaps that's okay. Understanding doesn't always mean having a mental picture. Sometimes it means having equations that work and predictions that match observation, even if the phenomena they describe remain strange to our evolved intuitions. So we end up in a place of knowing and not knowing simultaneously. We know the universe is expanding. We have equations describing that expansion. We've verified those equations observationally. But we don't fully understand what space is or why it has the properties it does. We can't visualize expansion without falling back on potentially misleading analogies. We can't answer every why question that arises, and that's the current state of human knowledge, a mixture of hard-won understanding and persistent mystery, and there's beauty in both. One of the most important lessons from studying the universe is that reality doesn't have to make intuitive sense to us. Our intuitions evolve to help us navigate the middle-sized world of everyday objects, not to comprehend black holes or quantum fields or expanding space-time. When physics tells us things that violate common sense, the problem is usually with our sense, not with physics. Learning to accept this strangeness, to let go of demanding that the universe conform to our expectations, is part of developing a scientific worldview. Quantum mechanics is famously counterintuitive. Particles exist in superposition of states until measured. Entangled particles share correlations that seem to violate locality. The act of observation affects what's observed. These aren't quirks or mistakes in the theory. They're features of how reality actually works at small scales, verified by countless experiments. They violate our intuitive picture of how things should behave, but that picture was never guaranteed to apply at all scales. Relativity is similarly strange. Time passes at different rates for observers in different reference frames. Space and time are not separate but unified into space-time. Simultaneity is relative, not absolute. Gravity isn't a force but a curvature of space-time. These ideas seemed bizarre when Einstein first proposed them, and they still feel bizarre today if you really think about them. But they're true, or at least they're our best description of how things actually work, supported by overwhelming evidence. Cosmic expansion fits into this pattern. Space itself expanding, distances growing without objects moving through space, the universe not expanding into anything. These seem counterintuitive because they don't match our everyday experience. But the universe isn't obligated to match our experience. It's vastly larger, older, and stranger than anything we encounter directly. If we're surprised that it behaves in ways we don't intuitively expect, that says more about the limits of our intuition than about any deficiency in reality. Accepting this requires a kind of intellectual flexibility, a willingness to update our mental models based on evidence even when the new models feel uncomfortable. It's easy to reject ideas that seem to violate common sense, to insist that there must be a more intuitive explanation. But history shows that clinging to intuition over evidence leads to error. The Earth seems flat and stationary, but it's round and moving. The Sun seems to orbit Earth, but it's the other way around. Common sense is often wrong about how the universe works. This doesn't mean we should abandon all intuition or accept every counterintuitive claim uncritically. Intuition is useful, and extraordinary claims require extraordinary evidence. But when multiple lines of evidence all point to the same conclusion, when the mathematics is clear and the observations consistent, when the counterintuitive idea fits into a broader theoretical framework that's been extensively tested, then it's time to accept that reality might be stranger than we first imagined. For cosmic expansion, the evidence is strong. Galaxies recede with speeds proportional to distance. The cosmic microwave background shows expansion's signature. General relativity, tested in countless other contexts, predicts expansion given the universe's matter and energy content. The pieces fit together into a coherent picture that's been refined over decades of observation and theoretical work. The fact that expansion doesn't require external space isn't a gap or mystery in this picture. It's a consequence of how space-time works according to our best theory. There's something almost liberating in accepting that the universe doesn't have to make sense to us in familiar terms. It removes the burden of trying to force everything into the boxes our minds came equipped with. We can appreciate reality on its own terms, strange and beautiful and unlike anything we'd have imagined if we were just making things up. The universe is under no obligation to be comprehensible to beings who evolved to throw spears and forage for food. The fact that we can understand it at all, even partially, is remarkable, and this acceptance of strangeness doesn't diminish the sense of wonder, it enhances it. If the universe were just a bigger version of our everyday world, if everything worked the way we intuitively expected, it would be far less interesting. The genuine strangeness of quantum mechanics, the counterintuitive nature of relativity, the impossible-seeming features of cosmic expansion, these are what make exploring the universe endlessly fascinating. Every time we think we've got it figured out, reality reveals another layer of strangeness we hadn't anticipated. So when we say the universe isn't expanding into anything, we're not being evasive or obscure. We're reporting what the mathematics and observations tell us, even though it feels strange. And we're inviting you to accept that strangeness, to let go of the expectation that expansion must work like everyday expansion, to sit with the discomfort of a reality that doesn't fit familiar patterns. It's in that discomfort, that willingness to update our intuitions, that real understanding begins. Let this acceptance of the universe's strangeness rest gently as we consider what expansion means for the deepest questions about existence and meaning. Stepping back from the details of expansion and geometry, Let's think about what cosmic evolution means for how we understand our place in existence. We're living in an expanding universe that emerged from a hot, dense beginning nearly 14 billion years ago, that's been growing and cooling and evolving ever since, that will continue expanding into an unimaginably distant future when everything will be dark and cold and separated. This is the cosmic context of our existence, and it's worth contemplating what it means. One reaction to cosmic expansion is a sense of insignificance. The universe is so vast, we're so small, everything we care about occupies such a tiny corner of space and time. Earth is a speck in a galaxy that's one of hundreds of billions, and that galaxy is receding from countless others as space expands. In the grand scheme, we barely register. Our entire civilization is a brief flicker in the long history of cosmic evolution. This can feel diminishing, as if our lives and concerns don't matter against such scales. But there's another perspective. We're part of the universe observing itself, matter organised in such a way that it can contemplate its own origins and nature. The universe has existed for billions of years before humans evolved, and it will continue for unimaginably longer after we're gone. But in this brief moment, on this small planet, consciousness has emerged and is looking outward, asking questions about space and time and expansion. That's remarkable, perhaps even precious. The atoms in our bodies were forged in stars that lived and died before the sun formed. We're made of stardust, quite literally. Carbon and oxygen and iron created in stellar furnaces and scattered by supernovae, later gathered into new solar systems and planets. We're not separate from the cosmos, we're expressions of it, particular configurations of matter and energy that the universe has taken for a brief time. When we study cosmic expansion, we're studying our own origins, the processes that led to galaxies forming and stars igniting and planets coalescing and life emerging. Cosmic expansion also gives us a deep time perspective that can be both humbling and clarifying. The concerns of daily life, the anxieties and frustrations seem smaller against the backdrop of cosmic history. Not in a way that makes them meaningless. Our experiences matter to us and that's enough, but in a way that provides context. Whatever struggles we face individually or collectively, the universe has been evolving for billions of years and will continue regardless. There's a kind of peace in that, in knowing that the cosmos doesn't depend on our successes or failures. At the same time, the cosmic perspective reveals how special our current moment is. We exist during a brief window when stars are still forming, when galaxies are visible across the universe, when the evidence of the Big Bang is still accessible. In the far future, intelligent observers, if any arise, won't have access to this evidence. They'll see an apparently empty, static universe with no indication of its dynamic history. We're privileged to live when the universe is revealing its story to those who know how to look. This connects to questions of meaning and purpose. If the universe is expanding, if it had a beginning and will have an end, if we're temporary structures in a vast impersonal cosmos, does anything matter? Does life have purpose in a universe governed by physics rather than providence? These are questions science can't answer directly because they're about values rather than facts. But the cosmic context can inform how we think about them. One view is that meaning is something we create rather than discover. The purpose comes from our goals and values and relationships rather than being written into the fabric of reality. The universe doesn't care what we do, but we care, and our caring is what matters. We give our lives meaning through what we choose to value, how we treat each other, what we create and explore and experience. The absence of cosmic purpose doesn't diminish human purpose. It just means purpose is a human concern rather than a universal one. Another view is that there's meaning in understanding itself, that the fact we can comprehend cosmic expansion and evolution is itself significant. The universe has produced beings capable of figuring out how it works, and there's something profound in that. Knowledge is valuable not because it serves some external purpose, but because understanding is inherently worthwhile. We study cosmic expansion, not because it will change the expansion, or because the universe cares what we discover, but because we care, because we're curious, because understanding is one of the highest achievements of consciousness. Perhaps both views are right in different ways. Meaning is what we make it, and one thing we can choose to find meaningful is understanding the cosmos we're part of, studying expansion, contemplating what it means for space to grow without external space, wrestling with these deep questions about reality. This is how some humans choose to spend the brief time we have, and there's beauty in that choice, in directing our attention outward to the largest questions we can ask. The universe is expanding, and we're here to witness and understand it, at least partially. That's the cosmic perspective, a mixture of humility about our smallness and wonder at our ability to comprehend, acceptance of our temporary existence, and appreciation for the brief moment we have to observe and think and explore. As we near the end of this journey through cosmic expansion, it's worth acknowledging that some mysteries may persist regardless of how much we learn. Not all questions have answers, or at least not answers we can discover with the tools and perspectives available to us. Learning to live with mystery, to be comfortable not knowing, is part of developing a mature relationship with knowledge and the universe. The question of what the universe is expanding into might be one of those persistent mysteries, not because we lack data or theory, but because it's asking for something that might not exist. We've seen how general relativity describes expansion as an evolution of space-time geometry requiring no external space, and how observations confirm this theoretical framework. But the question persists in our minds because it seems like there should be more to the story. Like underscore underscore quote underscore 35 underscore underscore can't be the complete answer, even if it's technically correct. Perhaps this persistent sense of incompleteness is telling us something important. Maybe there are aspects of reality that lie beyond our current conceptual frameworks, structures or dimensions we haven't discovered yet that would make expansion seem less mysterious. Or maybe the sense of incompleteness is just our intuition protesting against a truth that genuinely doesn't fit our evolved patterns of thought. It's hard to know which without future discoveries that might never come. What we can do is hold multiple perspectives simultaneously. We can accept that within general relativity, expansion requires no external space, while also acknowledging that general relativity might not be the final theory, that quantum gravity or something beyond it might reveal deeper structure. We can be confident in what observations and well-tested theories tell us while remaining open to the possibility of future revisions. This is how science actually works, building on current understanding while staying flexible about what future evidence might reveal. Living with mystery also means being comfortable with the provisional nature of knowledge. Everything we think we know could potentially be overturned by new evidence, though the more well-established something is, the less likely major revision becomes. The expansion of the universe is extremely well-established, but the interpretation of what expansion means, what space really is, these are areas where current understanding might be incomplete. We should hold our current answers firmly but not so tightly that we can't let go if better answers emerge. There's also the mystery of our own existence and consciousness within this expanding universe. How did matter organised by physical law give rise to beings capable of contemplating that law? How does consciousness fit into a cosmos of quantum fields and curved space-time? We don't have good answers to these questions, and they might be even deeper than the mysteries of cosmic expansion. The fact that we're here asking questions is perhaps the deepest mystery of all. But mystery doesn't mean ignorance. We've learned an enormous amount about cosmic expansion, about the universe's history and composition and future. We have a mathematical framework that describes expansion with extraordinary precision. We've verified predictions, tested hypotheses, built up a coherent picture supported by multiple independent lines of evidence. This is real knowledge, even if it's not complete knowledge, even if questions remain. The key is balancing confidence in what we know with humility about what we don't. We know the universe is expanding. We know expansion is accelerating due to dark energy. We know space itself is dynamic, not a static background. We know general relativity describes this expansion as evolution of space-time geometry, requiring no external space. These are solid conclusions based on observation and theory. What we don't know is why dark energy exists, what happened at the absolute beginning, whether there are aspects of reality beyond what current physics describes. And we should be honest about these gaps without pretending they undermine what we do know. Living with mystery also means finding peace with uncertainty. Not every question has to be answered for life to be meaningful or for knowledge to be valuable. We can appreciate what we understand while accepting that full understanding might remain forever beyond reach. The universe is under no obligation to be fully comprehensible to us, and there's something beautiful in that, in the humility it requires, in the ongoing invitation to keep wondering and exploring. So as we contemplate cosmic expansion and the question of what it's expanding into, we can hold the technical answer from general relativity, the philosophical puzzlement that persists despite that answer, and the acknowledgement that future discoveries might change our understanding all simultaneously. This is what intellectual honesty looks like, being clear about what we know, what we don't know, and what the difference is. We've travelled through 14 billion years of cosmic history, from the Big Bang to the far future, from quantum fluctuations to superclusters of galaxies, from mathematical equations to philosophical questions about existence and meaning. And we keep coming back to this question: what is the universe expanding into? We've approached it from every angle, examined the evidence, explored the theory, wrestled with the language and concepts. And the answer, strange and perhaps unsatisfying, remains the same. The universe isn't expanding into anything external to itself because space is the only something there is, and it's growing, and that's the complete description. Perhaps there's a kind of peace to be found in accepting this answer, even if it never quite fits comfortably in our minds. The universe is what it is. Reality doesn't conform to our expectations or intuitions. Space expands, distances grow, and no external arena is needed because space is fundamental, not embedded in something larger. This is what the mathematics says, what observations confirm, what our best understanding of reality tells us. And maybe that's enough. Acceptance doesn't mean we stop wondering or questioning. New observations might reveal aspects of cosmic expansion we haven't discovered yet. Future theories might provide a deeper explanation of what space is and why it has the properties it does. The question might transform into something more precise or more profound as our understanding develops. But for now, with the knowledge we have, the answer is clear, even if it's strange. Expansion is self-contained within the geometry of space-time itself. There's something almost Zen about this conclusion. The universe expands into nothing because there is no outside, no beyond, no container. It simply is, and it's growing. And asking what it's growing into is like asking what time existed before time began, or what's north of the North Pole. The question assumes a framework that doesn't apply. Accepting this requires letting go of the need for expansion to work like everyday expansion, letting go of the intuition that something growing must be growing into something else. This acceptance is part of a broader realization about our place in the cosmos. We're finite beings trying to understand the infinite, or at least the incomprehensibly vast. We're temporary structures trying to comprehend eternity. We're local observers trying to understand global properties. Of course we'll encounter limits, concepts that strain our ability to grasp them, answers that don't satisfy in the way we want them to. This isn't a failure. It's the natural consequence of our limitations meeting reality's scope. But within those limitations, we've accomplished something remarkable. We've figured out that the universe is expanding, traced its history back to the Big Bang, measured the expansion rate, predicted the far future. We've developed a mathematical framework that describes cosmic evolution with stunning accuracy. We've observed galaxies billions of light years away and understood what their recession tells us about space-time geometry. Persist. This doesn't diminish what we've persist. This doesn't diminish what we've learned. It just means the universe is deep enough to sustain ongoing investigation, rich enough to keep revealing new wonders. If we'd figured everything out, if there were no more questions, science would be finished and that would be sad. The persistent mysteries are what keep us engaged, what drive us to build better telescopes and develop new theories and think more carefully about the nature of reality. So we end our exploration here, not with final answers that close off all questions, but with the best understanding we currently have, honestly presented with its strengths and limitations acknowledged. The universe is expanding, and it's not expanding into anything external because expansion is an intrinsic property of space-time geometry. This is what observations and theory tell us, and while it may seem strange, while it may never quite feel completely satisfying, it appears to be true. And perhaps that's the ultimate lesson. Reality is under no obligation to make intuitive sense to us. It simply is what it is, strange and beautiful and vast beyond comprehension. Our job isn't to demand that it fit our preconceptions, but to observe carefully, think clearly, and accept what we find even when it challenges our intuitions. This is what science does at its best, revealing truth that's often stranger than fiction, showing us a universe more wonderful and mysterious than we could have imagined. Let's carry this sense of wonder and acceptance forward as we prepare to close our journey and settle into rest. We've travelled together through 2.5 hours of cosmic exploration, you and I, drifting slowly through questions about expansion and space and what it means for the universe to grow without growing into anything external. Thank you for staying with me through this entire journey, for giving your time and attention to these deep questions about reality. I know 2.5 hours is a significant commitment, and I'm grateful you chose to spend that time here, contemplating the nature of cosmic expansion. From the initial observation of receding galaxies to the theoretical framework of general relativity, from the Big Bang's beginning to the far future's cold darkness, from mathematical descriptions to philosophical puzzles about existence and meaning, we've covered vast territory. We've explored how space itself can expand, how that expansion doesn't require external space to expand into, how the question itself might be based on intuitions that don't apply to the cosmos as a whole. We've examined the evidence, wrestled with the language, accepted the strangeness, and found some measure of peace in acknowledging that reality doesn't have to make intuitive sense to be true. The answer to our central question, as honestly as I can give it, is that the universe isn't expanding into anything because there is no anything for it to expand into. Space is the metric. The metric is evolving, and that evolution is expansion. No external space is needed, no container, no beyond. This is what general relativity tells us, what observations confirm, what our best understanding of reality suggests. It's a strange answer, one that may never feel completely satisfying. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. One that may never feel completely satisfying, because it violates our everyday intuitions about how expansion works. But the universe is under no obligation to conform to our intuitions, and sometimes the truth is stranger than we expect. Perhaps the deeper truth is that some questions reveal more through the asking than through any answer we might give. Wrestling with what the universe expands into has led us through cosmic history, theoretical physics, the nature of space and time, the limits of language and knowledge, questions about meaning and existence. The journey matters as much as the destination, and I hope the journey has been worthwhile even if the destination remains somewhat puzzling. If you enjoyed this slow drift through cosmic mysteries, a like truly helps this content reach others seeking the same peaceful way to end their day. And if you have thoughts or questions or ideas for future explorations, the comments are always open. I read them, I appreciate them, I learn from them. To those already subscribed, thank you for being part of this community of curious minds, for coming back to explore the universe together. Wherever you are in the world right now, I hope you're comfortable. I hope you're warm or cool as you prefer. I hope your breathing has slowed and deepened over the past 2.5 hours. I hope your thoughts have quieted, at least a little, and that the concerns of the day have faded into the background as we've contemplated these larger questions about cosmic reality. I hope you feel some sense of wonder at the universe we're part of, some appreciation for how strange and beautiful existence really is. Look up at the night sky, if you can, if the weather permits and the lights aren't too bright. Or imagine it if you can't see it directly. All those stars, all those galaxies, all that space stretching between them, growing larger every moment as the universe expands. And you're here, made of atoms forged in ancient stars, conscious and aware, able to contemplate these cosmic mysteries. Every photon that reaches your eyes has travelled through expanding space, stretched by the growth of the universe itself, carrying information about distant worlds and ancient times. You're connected to all of it, part of the same cosmic evolution that began nearly 14 billion years ago and continues today. The universe is expanding, and perhaps that's the most important thing to remember. It had a beginning, it's evolving, it will continue into an unimaginably distant future. We're here for the briefest moment in that long history, privileged to observe and understand, to ask questions and find some answers, to wonder at the strangeness of it all. Nothing we do will change the universe's expansion. The cosmos will continue regardless of our struggles and achievements. But we're here, we're thinking, we're trying to understand, and that's enough. That's meaningful in itself. There's a kind of peace in accepting that the universe is larger and stranger than we can fully comprehend, that some mysteries may persist despite our best efforts, that reality is under no obligation to make sense to us. We can do our best to observe carefully and think clearly. We can develop theories and test them against evidence. We can build up understanding step by step. But we should also be humble about the limits of our knowledge, honest about what we don't understand, comfortable with the mystery that remains. Space is expanding into nothing because there is no outside, no beyond, just the continuous evolution of space-time geometry. It's strange, it challenges our intuitions, it may never feel fully satisfying. But it's what the evidence and theory tell us, and sometimes truth is stranger than we imagined. Accept it, sit with it, let it be strange. The universe doesn't need our permission to be what it is. Sleep well and dream of stars and galaxies separated by vast distances, all receding from each other as space itself grows, carrying them along on the tide of cosmic expansion into an ever larger universe. Dream of photons stretched by expanding space, of the cosmic microwave background cooling over billions of years, of dark energy accelerating expansion into an unimaginably distant future. Dream of the brief moment in cosmic history when conscious beings emerged and looked outward and tried to understand where they came from and what it all means. Dream of the question that brought us together tonight and the strange answer we found, that the universe expands into nothing because nothing is all there is beyond the universe itself. Rest now. Let your body feel heavy and comfortable. Let your mind drift towards sleep without resistance. You've spent 2.5 hours contemplating cosmic mysteries, and that's enough for one night. The universe will still be expanding tomorrow. The questions will still be there. But for now, just rest. Sleep deeply and peacefully. Good night.